All right, we are going to talk about how to find the long-run distribution for a Markov chain algebraically, and we're only going to do this in a 2x2 case. And so we have here a transition matrix for a 2x2 system, and we can call the states A and B some sort of generic names, right? So we remember how this works. It says this 0.4 is telling me that in any one round, whatever the round means, there's a 0.4 chance to end up at A. And so the way we work, know that if we are in the long-run distribution, sometimes called the equilibrium distribution, that no matter where we are, no matter what x and y are, when we apply the transition matrix to it, we're just going to end up back at the same spot. And so this is sort of the key setup for finding the long-run distribution algebraically. And so now I'm going to multiply these matrices, and so I'm going to match up the first row and first column. And so 0.4x plus 0.1y, and then I'll match up first row and second column, and so 0.6x plus 0.9y. And this has to equal the other side, and the other side is xy. Well, the only way two matrices are equal is if their first slots are equal, and their second slots are equal. And so I know that 0.4x plus 0.1y has to equal x. So here's the interesting thing. I also know that 0.6x plus 0.9y has to equal y. I'm not going to actually bother writing that one down because there's actually no new information in that. Once I have this first equation, I automatically know the second equation, and that's because the rows in my original matrix always add up to 1. And so I don't actually need that second equation because there's no new information in it. But this is problematic because I now only have one equation and I have two variables. And so I do need a second equation if I want to figure out exactly what x and y are. And my second equation is always going to be the same thing. It's always going to be x plus y equals 1. And the reason that works is because we know that the total of all the things together has to equal 100%. And so x plus y always has to equal 1. And so now I'm going to solve this system by hand. And the way to solve this by hand is I'm going to get all the x's on one side in this equation. And so now I'm going to have negative 0.6x plus 0.1y equals 0. And then I have this as my other equation, x plus y equals 1. And so this is my 2x2 system that I'm going to solve. And I'm going to choose to solve it by elimination. And so I'm going to take this equation and multiply by 0.6. So that gives me 0.6x plus 0.6y equals 0.6. And then my first equation is still negative 0.6x plus 0.1y equals 0. I can now add those two equations together. The x's cancel out. I get 0.7y equals 0.6. So y equals 0.6 over 0.7, which is 6 over 7. And then I need to know what x is, and x is going to be, we know that x plus y equals 1, so x plus 6/7 equals 1. So if I subtract 6/7 from both sides, I get 1/7. And so I guess up at the top, if I was calling this A and B, so now I know that in the long run, A is going to be 1/7 and B is going to be 6/7. And you could check this on your calculator by taking that transition matrix that we originally had and raising it to a high power like 100, multiplying that by any initial matrix. And when you do that, you should get this distribution of 1/7 and 6/7. Hopefully that's helpful.